On April 11, 1986, a radiation therapist at the East Texas Cancer Center in Tyler sat down at a keyboard to treat a man for a skin cancer on the side of his face. Her prescription called for an electron beam at 10 million electron volts. She entered the treatment data quickly, having done it hundreds of times before. Noticing that she had typed the letter for X-ray mode instead of the letter for electron mode, she moved the cursor up, corrected the single character, and pressed the return key several times to bring the cursor back to the command line. All of that took her less than 8 seconds. Her screen reported the parameters verified and the beam ready, so she turned the beam on. Within a few seconds, the machine stopped itself and displayed the words, "Malfunction 54." A loud noise came over the intercom. The patient told her that something had struck him on the side of the face, that he had seen a flash of light, and that he had heard a sound like frying eggs. He died on May 1st, 1986, 3 weeks after the treatment. An autopsy found acute high-dose radiation injury to the right temporal lobe of his brain and to his brainstem. Nothing in the accelerator had broken. Every switch, magnet, and circuit did what it had been built to do. 8 seconds of ordinary typing had opened a gap inside a computer program, and that program was the only thing standing between a cancer patient and the raw accelerator beam. The Therac-25 was a medical linear accelerator, one of the machines hospitals used to aim radiation at a tumor. Inside it, electrons are driven to enormous energies and delivered to the body in a narrow beam. Shallow tissue can be treated with those electrons directly. Deeper tumors need something more penetrating, so the electron beam is fired into a metal target, which converts it into X-ray photons. That last sentence contains the whole danger of the machine. A dual-mode accelerator does two completely different jobs along the same beamline, and the settings for one are lethal in the other. In electron mode, the beam is deliberately weak, and scanning magnets spread it out before it reaches the patient. Photon mode raises the beam current roughly 100 times, because the target and the beam flattener behind it, a very efficient attenuator shaped like an upside-down ice cream cone, absorb most of the energy before any of it reaches skin. Remove the target and the flattener from the path while the current is still set for X-ray work, and a patient receives the unattenuated beam. Which configuration was in place depended on a turntable. Bolted to it were the scanning magnets for electron mode, the target and flattener for photon mode, and a stainless steel mirror that shone a light onto the patient to show the operator where the beam would land. 3 microswitches reported to the computer which of the 3 positions the turntable had reached. Atomic Energy of Canada Limited built the Therac-25, and it was not the company's first. During the early 1970s, AECL had gone into business with the French firm CGR to build linear accelerators. 2 products came out of that partnership. The Therac-6 produced X-rays only at 6 million electron volts. Its successor, the Therac-20, was a dual-mode machine at 20 million electron volts. Both were computerized versions of older CGR designs, the Neptune and the Sagittaire, controlled by a PDP-11 mini-computer from Digital Equipment Corporation. Something important separates those 2 earlier machines from the one that followed. On the Therac-6 and the Therac-20, the computer was a convenience. Underneath it sat equipment capable of standing alone, whose industry-standard hardware safety features and interlocks were retained. Independent protective circuits watching the electron beam scanning, mechanical interlocks policing the machine. If the program made a mistake, wire and metal caught it before a patient did. By the middle of the 1970s, AECL had an idea of its own, a double-pass design that folded the long acceleration path back on itself, reaching comparable energy in far less space and at lower cost. Around that concept, the company designed the Therac-25, one machine that could deliver photons at 25 million electron volts, or electrons at a range of energies, so that a hospital needed a single unit for both kinds of treatment. A hardwired prototype existed in 1976. Competitive pressure ended the arrangement with CGR when the cooperative agreement came up for renewal in 1981, and the completely computer-controlled commercial version became available in late 1982. Here is the decision the entire story turns on. Rather than building on a machine with a clinical history of its own, AECL designed the Therac-25 for computer control from the outset, and, in the words of the investigation that later explained the accidents, took advantage of the computer's abilities and decided not to duplicate all the existing hardware safety mechanisms and interlocks. Software checks were substituted for many of the traditional electromechanical interlocks. Those independent protective circuits that had watched the beam on the Therac-20 were simply absent. Worse, the software doing the watching was not new. AECL's own quality assurance manager wrote to a customer that the same Therac-6 package was used when the company started the Therac-25 software, and that the Therac-20 and Therac-25 programs had been done independently from a common base. He appears to have been unaware of something discovered only later. Routines from the Therac-20 had been borrowed as well to handle electron mode. Code written for machines whose hardware would catch its errors was carried into a machine that had no such hardware. What ran that code was modest, even by the standards of 1982. Written specially for the machine, the real-time executive ran in 32 kilobytes on a PDP-11 in assembly language, with no standard operating system underneath it. Operators worked at a VT100 terminal, typing each patient's prescription into a form on a green screen. One more design choice belongs here. Early operators complained that entering a treatment plan took too long, so AECL modified the software before the first unit was installed, letting a quick series of carriage returns copy the treatment site data instead. That change, made to save keystrokes, would figure in several of the accidents. 11 Therac-25 machines were installed in all, 5 in the United States and 6 in Canada. Measured in units, that is a small population. Judged by the confidence invested in it, the machine stood extremely high, and that confidence is the thing to understand before the rest of the story makes sense. Consider what AECL believed about its own product. During March 1983, the company performed a safety analysis on the Therac-25 in the form of a fault tree, and that analysis apparently excluded the software. Its stated assumptions recorded that programming errors had been reduced by extensive testing, and that residual software errors were not included. Where the tree did reach for a number, it assigned the event computer selects wrong mode, a probability of 4 in 1 billion. No justification for that figure appears anywhere in the report. Hospitals believed it too, and they had reason to. Patients were treated successfully, day after day, for years. At the East Texas Cancer Center, the machine had been in service for 2 years by March 1986, and more than 500 patients had been treated on it. Nancy Leveson's summary of that record is the most uncomfortable sentence in the whole investigation. The software was highly reliable, and it worked tens of thousands of times before overdosing anyone. Testing carried the same false weight. Asked at a users meeting how much the software had been tested, AECL's quality assurance manager answered 2,700 hours. Pressed by the users in the room, he clarified that he meant 2,700 hours of use. Then, there was the arithmetic of reassurance. Having redesigned a turntable microswitch in September 1985, AECL told its customers that analysis of the hazard rate indicated an improvement over the old system by at least 5 orders of magnitude. A medical physicist at Yakima Valley Memorial Hospital, reading that letter of September 16, 1985, converted the claim into plain arithmetic and wrote it out as 10 million%. With an improvement of that size, he explained afterwards, his department did not believe there could have been any accelerator malfunction. Every one of those numbers described the hardware, none of them described the program. A race condition is one of the least forgiving failures in software, and the phrase deserves precision. Programs of this kind do several things at once. On the Therac-25, a task called treat ran a treatment through a sequence of phases, while a separate keyboard handler task ran alongside it, reading whatever the operator typed. They communicated by leaving notes in shared memory, a flag saying data entry was complete, and a 2-byte variable holding the mode and energy the operator had selected. Correct behavior depended entirely on the order in which those notes were written and read, and nothing enforced an order Whichever task reached the memory first decided what happened next. That is a race condition. Identical code, identical inputs, and a different outcome depending only on timing. Now, put a human being inside the timing. The 2 bytes holding mode and energy were split. Reading the low byte, a third concurrent task physically drove the turntable to the position for the selected mode. The data entry routine read the high byte and loaded the machine's operating parameters from a calibration table. Inside that routine, a subroutine called magnet set the bending magnets, and setting the bending magnets takes about 8 seconds. To pass the time, magnet repeatedly called a timing routine that also checked whether the operator was editing anything. Checking for edits, however, depended on a flag that the timing routine cleared on its very first pass. From then on, every edit was invisible to the data entry routine, while remaining perfectly visible on the screen in front of her. Follow what that meant for the woman at the keyboard in Tyler. She typed X-ray, saw her mistake, moved the cursor up, typed electron, and pressed return. All inside the 8 seconds, the magnets were still settling. The turntable task read the low byte and swung the turntable into electron position. Meanwhile, the data entry routine never learned that anything had changed and kept the operating parameters it had already loaded for X-ray mode. Beam current for photon therapy is roughly 100 times that used for electron therapy, and the target and flattener meant to absorb it were no longer in the path. Simulations of the first Tyler accident later indicated doses of 16,500 to 25,000 rads in under 1 second across about 1 square centimeter. A single therapeutic dose in 1986 was in the region of 200 rads. Worse still, the machine could not tell. Ion chambers were supposed to measure what had been delivered, but they could not handle the ionization density of an unscanned beam at full current, so they saturated and reported a low dose. The console therefore showed 6 monitor units where 202 had been requested, and offered a treatment pause. Press 1 key and carry on. Here, the popular version of this story goes wrong. Most retellings reduce the Therac-25 to a single unlucky bug, as though a more careful programmer would have prevented 6 catastrophes. Lev Ason's finding is harder than that. Focusing on particular software bugs, she wrote, is not the way to make a safe system. The basic mistakes were poor software engineering practice and building a machine that relies on software for safe operation. Proof of that sits 1 model number away. The Therac-20 contained the same software error implicated in the Tyler deaths, and it injured nobody because its independent hardware protective circuits refused to let the beam turn on. 6 patients were massively overdosed between June 1985 and January 1987. 3 of them died of the radiation. The sequence matters as much as the total. June 3rd, 1985, at the Ken A. Stone Regional Oncology Center in Mary, ETA, Georgia. A 61-year-old woman receiving follow-up treatment after lumpectomy felt a sensation of heat and told the technician that she had been burned. She was told this was impossible. Her hospital physicist, Tim Still, telephoned AECL to ask whether the machine could run in electron mode without scanning. Engineers called back 3 days later to say improper scanning was not possible. Still later estimated that she had received 1 or 2 doses in the 15,000 to 20,000 rad range. Her breast was removed, her shoulder and arm were paralyzed, and she was left in constant pain. 7 weeks after Mary ETA, on July 26, 1985, a 40-year-old woman in Hamilton, Ontario, arrived for her 24th session. 5 times the machine shut down with the console reading no dose, and 5 times the operator pressed proceed. An AECL technician later estimated the delivered dose at 13,000 to 17,000 rads. The patient died that November of her cancer. An autopsy attributed her death to the disease and recorded that a total hip replacement would have been necessary had she lived. Unable to reproduce the fault, AECL blamed a microswitch, redesigned it, and produced the 5 orders of magnitude claim. Canada's Radiation Protection Bureau, through Gordon Simmons, instructed the company to make dose rate malfunctions terminate treatment outright. That instruction was not followed. The maximum number of retries was reduced from 5 to 3. December 1985, at Yakima Valley Memorial Hospital in Washington, a woman developed reddening on her hip in a parallel striped pattern. and staff x-rayed her electric heating pad to see whether its wires matched the marks. They did not. On February 24, 1986, AECL's technical support supervisor wrote to the hospital that the damage could not have been produced by any malfunction of the Therac-25 or by any operator error, and set out 2 pages of technical reasons why an overdose was impossible. Recorded cause: unknown, March 21, 1986, Tyler, Texas. Malfunction 54 appeared twice, while the treatment room's video monitor sat unplugged and its audio monitor sat broken. Engineers tested for a day without reproducing the fault, and the engineer sent from head office reportedly explained that it was not possible for the Therac-25 to overdose a patient. Asked directly whether there had been other overexposures, AECL personnel said the company knew of none 7 months after Hamilton. That patient died of his injuries 5 months later. Back in service on April 7, 1986, the machine killed a second man 4 days after that. Breaking the case took one physicist's stubbornness. Fritz Hager, the hospital physicist at Tyler, pulled his machine out of service and sat with the operator until she had reconstructed precisely what her hands had done. Between them, they established that editing speed was the trigger, and Hager practiced until he could produce Malfunction 54 at will, told by an AECL engineer that the error could not be reproduced. Hager explained that the sequence had to be performed quite rapidly, and the company finally reproduced it on its own machine. 2 days after the April accident, AECL measured 25,000 rads at the center of the field. The frying sound the patients had described, an engineer explained, was the ion chambers saturating. January 17, 1987, Yakima again, and a different fault entirely. This patient was prescribed 86 rads in total. Setting up the machine ran a routine that incremented a 1-byte counter on every pass, several hundred times per setup. 1 byte holds a maximum of 255, so on every 256th pass, the counter rolled over to 0, and a 0 told the rest of the program that the upper collimator had already been checked and was fine. Pressing the set button at exactly that instant, the operator turned on a full 25 million electron volt beam with the turntable still in the field light position. No target, no flattener, no scanning, and a stainless steel mirror directly in the path. Preliminary measurements put the dose at 4,000 to 5,000 rads per attempt, and there were 2 attempts. The patient died that April of complications from the overdose. AECL's own quality assurance manager told the FDA that the changes already designed after Tyler, 9 months earlier, and still not installed, would have prevented it. The company's first remedy reached customers on April 15, 1986, the same day it filed its accident report with the FDA. That remedy was a letter instructing every hospital that the cursor-up key must not be used for editing or anything else, that its keycap must be removed, and that its switch contacts must be fixed open with electrical tape. Regulators were unimpressed. On May 2, 1986, the FDA declared the machine defective and demanded a corrective action plan, and the agency's director of compliance wrote that the company's letter did not describe the defect nor the hazards associated with it, and that its tone was not commensurate with the urgency. Obtaining an adequate plan took more than a year and 5 revisions. AECL informed the FDA in September 1986 that no single test plan existed for the software. Following the second Yakima overdose, Ed Miller of the FDA telephoned his Canadian counterpart on February 6, 1987, to say the agency would recommend that every Therac-25 be shut down. On May 26, 1987, the FDA rated the action a Class 1 recall, the category reserved for products with a reasonable probability of causing serious injury or death. The final corrective action plan, issued on July 21, 1987, is the most eloquent document in the case because of what it put back. Dosimetry faults now suspended treatment instead of pausing it. A potentiometer independently reported the turntable's true position. An independent hardware circuit stopped the beam after a single pulse of excessive energy, without asking the software's permission. Editing was restricted to 3 keys, and 23 further software changes followed. Nearly every significant protection on that list is a hardware interlock of the kind the Therac-20 already had. No Therac-25 accident has been reported since the plan was implemented. Every lawsuit was settled out of court, so no judge ever ruled on the merits. Hospitals were not even obliged to report device injuries at the time. The United States General Accounting Office told Congress in November 1989 that a study of 10 hospitals found the FDA aware of less than 1% of device problems. Congress closed that hole with the Safe Medical Devices Act, signed on November 28, 1990, which gave hospitals 10 working days to report a device-related death. AECL's medical division was privatized as Therac-25 International. MDS bought it outright in 1998, and AECL returned to building nuclear reactors. Nancy Leveson and Clark Turner published their investigation in IEEE Computer in July 1993, and it has been assigned reading in software engineering courses ever since. Leveson is now professor of aeronautics and astronautics at MIT. When the international standard IEC 62304 appeared in 2006 to govern the whole life cycle of medical device software, it was answering questions this machine had raised 20 years earlier. 8 seconds is not an unusual amount of time. It is roughly how long an experienced person needs to correct one character and carry on. On the Therac-6 and the Therac-20, an operator could type that fast every working day of her career, and nothing would happen because a protective circuit of wire and metal sat between the program and the beam, and it did not care how quickly anybody typed. Removing it saved money and saved space, and it moved a life-or-death judgment into a program running in 32 kilobytes, for which no single test plan had ever been written. Through the summer of 1986, in 11 hospitals across 2 countries, there were keyboards with one key cap pulled off and the contacts underneath sealed with electrical tape. That was the safety system for a while, a piece of tape over an arrow, because the software beneath it could not be relied upon to notice that a human being had changed her mind. Every safety-critical software standard written since exists, so that no patient is ever again protected by a piece of tape. Subscribe.